Hello everyone, I'm Tyler Kibler, a graduate student attending Virginia Tech, and I will be discussing MOPT, Optimized Mutation Scheduling for Fuzzers. First, I want to discuss basic fuzzing. Fuzzing, as we likely all know, is a method of testing software input validation. This is done by feeding a piece of software various inputs, which are intentionally not what the software expects, in an attempt to create unexpected outcomes, such as crashes or revealing extra information. Fuzzers vary in the level of penetration of the software under observation, with some looking at abstractions of code to predict what code is being run, and others taking a much less involved approach, as you can see here. Mutation-based fuzzing is a fairly common form of fuzzing. It takes some initial test cases, called seeds, and alters them in an attempt to discover unexpected outcomes. This starts with a valid input, then alters them to create new test cases, which results in finding more vulnerabilities than fuzzing without starting data, especially with more complicated inputs. There are a few common mutation-based fuzzers, including AFL, libfuzzer, hongfuzz, and vuser. Among these, AFL was a fairly popular fuzzer, and as the website points out, it was easy to use, requiring nearly nothing in the way of tuning. However, it has not been updated since 2017 according to the website, whose URL is on screen now. Even by the time the paper was published in 2019, it had been unsupported for a couple of years, and some forks had already become reasonably popular, including AFL Fast and AFL++. The way that these systems operate requires a set of mutations, as well as a scheduler to select from those mutations. Often, these systems are very rigid, and the paper's authors felt that the existing dynamic schedulers did not do a sufficiently good job to justify their higher overhead compared to the existing models. There are reasons for this failure to reach optimal performance. The different operators that can be used to create test cases have varying efficiencies. Some operators are more likely to find crashes or vulnerabilities, so when selecting the next operator using a uniform distribution, as the current mutation fuzzers do, there will be a significant amount of time spent using inefficient operators. Operator efficiency will change with each program, therefore it would be highly difficult to efficiently identify the most effective operators for every program, so it is best to have the scheduler make decisions based on the operator's efficiency at runtime. In order to be useful as a fuzzer, and because it has to be determined at runtime, it is important that the most effective operators are decided on quickly. In regards to the scheduler efficiency, adding overhead to fuzzing runs counter to its goal of speed and efficiency, so any scheduler optimization needs to require few calculations. Also, because there are relatively few successes in fuzzing, and low numbers of successes would throw off many machine learning or gradient descent algorithms, this system should not use either of those strategies. Some quick background on mutation-based fuzzers. Mutation-based fuzzers are, quote, good at discovering vulnerabilities without utilizing prior knowledge of target programs, end quote. This line coming from the source paper. What they do instead is start with known good seeds and mutate those for further test cases. Their structure is made up of the following process. The fuzzer, which tracks seed test cases to be used, selects seeds in a certain order. It then mutates the seeds following some algorithm to create test cases, and then uses those test cases against the target program, reporting crashes or vulnerabilities, then begins again by selecting another seed, altering the order of seeds selected if necessary. Some fuzzers will collect much more runtime information about the target program, as mentioned before, during testing to assist with selecting more effective seeds and deciding how to mutate them. MOPT attempts to address concerns with that mutation selection process. It draws inspiration from particle swarm optimization, or PSO, dynamically analyzing the effectiveness of operators and changes their selection probabilities to reflect a more ideal selection rate. Each operator is subject to some minimum and maximum probability. Somewhere between these is that operator's, or particles, probability. That probability is updated locally during execution early on, and then assessed against other attempts to balance the particles' probabilities to create a new global distribution of operators. This scheme is to be applied to existing fuzzers just replacing the mutation scheduler with the MOPT scheduler. What are mutation operators? There are realistically infinite mutation operations, but for the most part, there is a set of operations that determine where and how these mutations take place. These operations are bit flip, where some number of bits are flipped, then skipped, then flipped, then skipped, and repeating that process. Byte flip inverts whole bytes, then steps over bytes, and then repeats that process. Arithmetic increment and decrement adds or subtracts a value from one byte or several bytes at a time. Interesting values, which inserts interesting values in place of certain bytes. User extras, which inserts user-provided tokens in place of some bytes, or just through insertion to some point in the test data. Auto extras, which overwrites bytes using token recognized during bit flip 1-1. Random bytes, which selects a random byte and sets it to a random value. Delete bytes, which deletes a random selection of several bytes. Insert bytes, which takes bytes from another test case, then insert them into a different location in the current test case. Overwrite bytes, which overwrites a random set of several consecutive bytes. And crossover, which combines two parts of two different test cases together. AFL derived fuzzers will all use a set of operations like these 11. Next is an explanation of the mutation scheduling scheme. AFL has 3 different scheduling stages. The deterministic stage scheduler, which uses 6 deterministic operators in order applied to each seed that is selected in that stage. Havoc stage scheduler, which determines a desired number of new test cases, then selects a series of operations using a uniform distribution for every desired test case, and performs the operations on the seed to create the desired test cases. Finally, there is the splicing stage scheduler, which uses the crossover operation only, then feeds the outcome to the Havoc stage scheduler for execution. The stage is only used when the other 2 schedulers haven't found anything after a round. Focus from here on out will be on improving the Havoc stage scheduler. Next, we will need to look at how not all operations perform equally. The authors tested the deterministic operations within AFL on a few programs to see how well they performed and how often each was chosen. Different operations have different efficiency on different programs, but for the most part, several variants of the bit flip and arithmetic increments generally produce the most interesting results, while some of the byte flips and larger arithmetic increments produced the least number of interesting test cases. The vast majority of the time in AFL is spent on the deterministic stage, despite the fact that the Havoc stage generally reveals more, and despite their efficiency in finding interesting test cases, bitflip 1/1 and bitflip 2/1 are run rather infrequently in the current AFL design. This all points to the need for a better mutation scheduler. MOPT could be that scheduler. The goal is to design a scheduler which will select operations at a rate to maximize how much they can find. Achieved using the PSO algorithm mentioned earlier, PSO was originally designed to find optimal solutions while considering momentum to prevent overfitting at the local optimum and also be computationally simple. Unlike PSO, which explores particle optimization for single problem spaces, this alteration of PSO places each operator, called the particle, in this case, in their own probability space and are allowed to move about that space independently from other probabilities. In MOPT, each operator is a particle in a space between some minimum and maximum, with the value being the probability that the particle is chosen and the sum of all particles' probabilities being normalized to 1 when they are finally brought into the same probability space at the end of the optimization period. The local bests are stored along the way and compared with current results by looking at if the same number of calls were made to each, would they have discovered the same number of interesting test cases. If the new is better than the local best, by this definition, then it becomes the new local best. 2 quick notes: local efficiency is the ratio of interesting test cases to the total number of test cases. Also, interesting outcomes generally seem to be program crashes, though in some cases other interesting outcomes are specified in the paper. Generally, it is crashes. The global best positions are what is really used to determine the probability of a particle being selected in MOPT and is based on their global efficiency, which required analyzing multiple swarms of particles to find the best result. The swarms are made up of multiple particles, each exploring their own solution space. Swarm efficiency is the number of interesting test cases from that swarm divided by the total number of new test cases in an iteration. The most efficient swarm will have its probability distribution used for the scheduling implementation. For implementation, during the initial or pilot fuzzing phase, MOPT will use multiple swarms with different initial probability distributions. After the primary fuzzing period has finished, the total number of interesting test cases is evaluated, and that will affect the global efficiencies used for the remainder of the fuzz. This happens at the beginning of test case creation, allowing MOPT scheduler to be fitted into existing fuzzers with minimal alteration, so long as the scheduler can see how it is performing. MOPT is broken into a small series of modules. These are the initialization module, which sets the probabilities for the particles to a random value between 0 and 1, then normalizes all of them so they sum up to 1. Sets the velocity to 0.1, the efficiency of each particle to 0, the local best to 0.5, and the global best to 0.5, all across the swarm. Basically, it initializes values. Only needs to happen once when the fuzzer is first starting. Next is the pilot module, which creates the multiple swarms, evaluating them in order, stopping after it generates a specified number of test cases, measures the number of interesting test cases produced, the number of interesting test cases for a particular particle, and the invocations of that particular particle for each swarm. The swarm's efficiency is calculated from the division of the number of total interesting test cases found divided by the total number of test cases created. Next, core fuzzing module takes the best performing swarm and uses that probability distribution for fuzzing, stopping when it generates the desired number of new test cases. In other words, the operators will have been chosen to create these test cases based on the ideal distribution derived during the pilot phase. The effectiveness of each operation is still being tracked. And finally, the PSO updating module. This module for updating swarms takes the results from pilot and core fuzzing modules and uses that to update the swarm values periodically. Now let's discuss the pacemaker mode. For AFL-derived fuzzers, this skips the deterministic mode if MOPT has not found any new unique crashes or paths for a long time while mutating a particular seed. One benefit of this method is that it still keeps the deterministic stage enabled early on when it has the greatest benefit. However, as it is generally less effective for large parts of the fuzz, it is beneficial to disable it and operate primarily in the havoc stage. There is also an option to re-enable the deterministic stage if a certain amount of interesting test cases are found again. Alternately, it can stay off for the remainder of the fuzz after disabled, or not be used at all if desired. For the evaluation of MOPT, 13 open source Linux programs were fuzzed to evaluate the effectiveness of MOPT, which are a variety used in real-world settings and some are used in fuzzing research commonly. These are shown on the screen now. The authors compared AFL, MOPT, AFL temp, which is AFL, with the MOPT scheduler using the pacemaker in a mode where it can re-enable the deterministic stage after disabling it, and MOPT AFL ever, which is AFL using the MOPT scheduler, but once the pacemaker disables the deterministic stage, it will not be re-enabled again. Experiments were run on identical virtual machines using AFL version 2.52b. The VM has one core clocked at 2.4 GHz, 4.5 GB of RAM, and uses 64-bit Ubuntu version 16.04 LTS. The same setup will be used throughout all validation and testing unless otherwise noted, and the seeds consist of 100 files for their respective programs following their expected input formats. Large files for audio and PDF were split to make the seeds more reasonably sized, and evaluation will be done by tracking the number of unique crashes discovered by each fuzzer, with the number of unique paths discovered as a secondary metric if needed. For AFL, MOPT, AFL Temp, and MOPT, AFL Ever, they were run for 240 hours per program for all 13 programs. Both MOPT versions discovered over 2,000 more crashes than plain AFL, and they also covered significantly more unique paths, with Temp covering over 45,000 more, and Ever covering 56,000 more unique paths than AFL. In every case, they each discovered more crashes than AFL, with MOPT AFL Ever discovering the most crashes overall. And when we look at the number of vulnerabilities discovered, the vulnerability uniqueness was verified using address sanitizer to confirm that a crash happened with a different stack trace. And should a unique crash be discovered, the CVE website was checked to verify whether the crash was new. The MOPT systems discovered 81 security CVEs, 66 of which were new. Compatibility analysis. The MOPT scheduler has also been generalized to work with other fuzzers, such as AFL Fast and Vuser. Vuser focuses on code coverage, so MOPT needs to be slightly altered to promote exploring those deeper paths using fitness scoring to generate test cases. Vuser also has a different mutation strategy, generating a fixed number of test cases, but only keeping ones where the parent test case's fitness score was sufficiently high. Vuser has no deterministic phase, so there's no concern about needing to disable that, as there is with AFL. So there are three new fuzzers to evaluate: MOPT AFL Fast, Temp, MOPT AFL Fast Ever, and MOPT Vuser, which are tested on a subset of Linux tools used in the original test. Also, of course, they will be compared against AFL Fast and Vuser as well. With both alternative fuzzers, the MOPT versions generally discovered more unique crashes, though this does not seem to be true for absolutely everything. MOPT Vuser found more in MP4 to AAC, MP3 gain, SAM2P, and MPG321, but were not on EXIV2, TIFF2BW, or PDF images. MOPT generally performed better than the modern AFL-based fuzzers than on Vuser, finding many times the number of unique crashes, and due to implementation restrictions on Vuser, the test OS there was switched to 32-bit Ubuntu 14.04 LTS for both the Vuser and MOPT Vuser testing. Evaluations on Lava M. The Lava M dataset contains 4 programs with known and unknown vulnerabilities. It achieves this by injecting errors into existing programs. All the current models were tested on Lava M with an identical setup seed and run for 5 hours. MOPT AFL Ever was also used with Angora as well as with QSIM to construct MOPT Angora and MOPT QSIM, as well as AFL was used with them to get AFL Angora and AFL QSIM to evaluate their combined effects. QSIM is an evaluation tool which is designed to be used in conjunction with fuzzing tools in order to help them increase their code coverage, while Angora is a mutation-based fuzzer that seeks to increase code coverage without using symbolic execution using a search algorithm based on gradient descent. Again, across the board, MOPT implemented models outperformed their traditional counterparts, sometimes by considerable margins. The symbolic execution techniques used in Angora and QSIM are similarly improved with the assistance of MOPT, where their worst were performing just as well as their AFL counterparts, and generally at least a little bit better, if not significantly better. Moving on to steadiness analysis, this section was to provide a more comprehensive testing regimen and is set up and evaluated as follows. MOPT AFL Ever, AFL, Angora, and Vuser are all tested again against MP3 gain, PDF images, OBJ dump, JHead, and info2cap for 24 hours using the standard setup described earlier. Each test was run 30 times. There were 3 groups of experiments, each with different seeds. The first was a single file containing only the character lowercase a. The second had 20 seed files, and the third had 200 seed files. The seed files were retrieved from the internet and verified. Some were pared down as necessary if too large. To evaluate, the authors tracked the number of unique crashes and bugs. Bugs are being tracked using address sanitizer in the format described earlier. Moving on to the results, MOPT AFL ever discovered more unique crashes in 11 out of 13 test cases, and the p-values reinforce that there is significant evidence of improvement. Angora and Vuser find more unique crashes, but not bugs, when fuzzing MP3 gain in the 20 seed group. However, with JHead and OBJDump, the minimum for MOPT AFL ever was larger than the maximum for the other methods. The authors attribute this to the non-AFL method's deduplication strategies not working as well. Also, no fuzzer found any PDF images bugs or crashes during the A seed group, likely down to the complex nature of PDFs, meaning that while empty seeds created more test cases, they could not find much without a properly set up file to build off of. Next, we move on to stepwise analysis of MOPT, main framework, and pacemaker fuzzing mode, which focuses on the efficiency of the pacemaker mode to ensure that the benefits of MOPT are not entirely within its use of the pacemaker. We will be comparing AFL, AFL ever, which does not use MOPT but does use its pacemaker, the MOPT AFL off, which has MOPT but the pacemaker disabled, and MOPT AFL ever, which is using both MOPT and its pacemaker. They will be used against PDF images, W3M, OBJDump, and Info2Cap with an execution time of 24 hours. MOPT AFL off outperforms AFL, the pair without pacemaker mode, discovering more crashes despite MOPT being less used in this mode because of the large amount of time taken up by the deterministic mode. Similarly, MOPT AFL ever discovers more unique crashes than AFL ever, the pair with the pacemaker enabled, demonstrating that even with the pacemaker implementation, MOPT is a noteworthy improvement over AFL's scheduler. Evaluating the pacemaker mode, AFL ever discovered more crashes across the board than AFL, and only on PDF images did it have fewer unique paths. AFL ever does outperform MOPT AFL off regularly enough, however this is likely down to the time spent in that deterministic mode, not using MOPT scheduler despite being implemented. Using the pacemaker allows MOPT to outperform again, though, across the board with MOPT AFL ever compared to everything else. So, how quickly does MOPT identify the ideal distribution? Testing bitflip 1/1, arithmetic 8/8, and interest 16/8 on W3M and PDF images to see how quickly the probabilities converge toward their ideal. It was tested over the course of 240 hours on MOPT AFL ever. The convergence happens fairly quickly, within an hour on W3M, but iteration is initially much slower on PDF images because the deterministic stage is much more effective at finding errors here, leading to a notable delay in moving to the havoc stage, which MOPT runs in. That said, once MOPT takes over, the convergence is again very quick. Moving on to the overhead analysis, while the efficiency calculations for MOPT take more computing time compared to the normal AFL scheduler, this general downtick in total number of executed test cases is made up for by the efficiency of those test cases. There are some programs where MOPT AFL is able to also generate more test cases than AFL, and this is likely because MOPT has a higher probability of choosing less resource-intensive test cases when they turn out to find more bugs. Testing parallelization. To test how well MOPT parallelizes, AFL, MOPT AFL temp, and MOPT AFL ever were used to fuzz PDF images with a set of 20 PDF files for seeds, filtered using AFL CMIN to remove redundant test cases, with each having 3 instances labeled Fuzzers 1 through 3. Only Fuzzer 1 will perform the deterministic stage. The total CPU time for the experiments was over 70 days, with AFL discovering 1,778 unique crashes in that time, MOPT AFL temp discovering 2,907 crashes in that time, and MOPT AFL ever discovering 2,702 unique crashes within that time. MOPT AFL temp being able to re-enable the deterministic stage when it is beneficial allowed it to find more crashes than MOPT ever. This is to say that MOPT is at least as capable of parallel operation as AFL in general. So a quick review, MOPT demonstrates a measurable improvement to the existing scheduling algorithms for several mutation fuzzers related to AFL. It is able to find more unique crashes and bugs by focusing more on operations that are already producing results. Its benefits can be further increased by using its pacemaker mode to disable the deterministic stage when it is not being effective, and its design, being only the scheduling algorithm, means that existing effective fuzzers can implement it, though it is worth noting that the efficiency would need to be compared against the model's baseline, as the authors only extensively tested against AFL, vuser, and AFL fast. Thank you.